Hi and welcome back. We are going to start lesson 6 today, limits involving infinity, sometimes called limits at infinity, or asymptotes of graphs. So in a pre-calculus and college algebra course, you spend a significant time looking at vertical and horizontal asymptotes on a rational function. We're going to start with this lovely rational function right here, y equals 1 over x. We'll start with sort of a simple base case. Rather than just discussing its asymptotes, I'd like to look at the limit as x approaches infinity here in relation to horizontal asymptotes, see if we can sort of surmise something. So let's take a look at the limit as x approaches infinity, and I'm just going to write here of f of x. Tell me what you think that is. So I'm coming out all the way out, x is growing and growing infinitely large, and what's happening to those y values? They're getting smaller and smaller and smaller. So that would be 0. Okay, now let's try again. What's the limit, do you think, as x approaches negative infinity of this function? Well, as I'm going further and further and further out the x-axis to the left, what's happened to those y values? Well, they're getting smaller and smaller and smaller too, closer and closer and closer to 0. Although they may never reach 0, they're getting awfully close to 0. So that would also be 0. Okay. Let's take a look. Had to hit pause there, my computer was acting strange. So the graph of y equals 1 over x approaches 0. So we say the graph of y equals 1 over x approaches 0 as x approaches infinity or negative infinity. So let's take a look at the next figure. Okay, now with that first sketch, or that first graph, I didn't make us do anything algebraically. With this one, I mean, we just looked at it graphically and said the answer. With this one, we'll start off graphically, but we need to do it algebraically as well. So discuss the limit as x approaches infinity here, and then, show that algebraically. So here, we're coming on out, x's are getting larger, and what's happening to those y values? Well, they look like they're capping off here at about 5/3, okay? Same thing in the negative direction. Limit as x approaches negative infinity, those y values are climbing towards that 5/3, but don't look like they're going to cross it. And, we can put that in the TI and take a look, which we will, but I want to take a mathematical approach now. So, if I'm interested in the limit as x approaches infinity, first let's look at just positive infinity, of this function, 5x squared plus 8x minus 3 over 3x squared plus 2, what you want to do is you want to divide every term by the highest power in the denominator. So, alright, I'm going to do something and you'll probably see what I did pretty quickly. Oops, that should be a minus there. So you can see it looks like I'm taking every term in the numerator and dividing it by x squared. And the same thing's going to happen in the denominator. Every term in the denominator and dividing that by x squared. Because the highest power in the denominator of the variable, is x squared. Now, what happens is we want to investigate then the limit as x approaches infinity of every term in sort of now in the numerator and the denominator. Now I'm going to do this in another color. Here, let's clean this up. So x squared over x squared is going to cancel. X over x squared, you're going to be left with an x downstairs. Okay, here x squared over x squared is going to cancel. All right, now what I'd like to do then is gather what we're left with. Okay, so after all that, what would we be left with? I'm going to grab another color here. So after all that, I'm left with 5 plus 8 over x minus 3 over x squared all over 3 plus 2 over x squared. So I went from here to here. And again, the limit as x approaches infinity. Now a lot of people say, why don't you just store infinity now and for x and see what happens? And in essence, you kind of are doing that. So 8 over x, if x becomes very, very large, the expression 8 over x is going to shrink towards 0, right? So in other words, 8 over a huge number, over a huge positive number is awfully close to 0. Here, 3 over x squared, that's also going to go to 0, okay? Because 3 divided by a huge number is something awfully close to 0. 2 over x squared, also going to go to 0, okay, as x becomes infinitely large. And then after all that sweat equity, what are you going to be left with? You're going to be left with 5 over 3. So you're showing, we knew it graphically, that as x becomes larger and larger and larger, those y values are tending towards 5/3. But, now we're showing that algebraically, okay? Let's take a look at the TI. I did want to let you watch me type this in because a lot of people just simply type things in wrong. So notice that I needed parentheses. So parentheses 5x squared plus 8x minus 3. So I sort of chunk that off in parentheses, divided by 3x squared plus 2. Okay, take a look. I always like to do zoom 6, my standard window. And there we are. Now what you can do is you can use the trace feature of your calculator to help you verify what's going on as x becomes larger and larger and larger. So what I do is I just go ahead and let that trace on out. So I hit trace with my, I'm moving that right arrow key all the way on out. My x's are becoming bigger and bigger and bigger, and look what's happening to my y values. They're going to 1.84, 83, you might be wondering, gee, how far are they going to go down? Well, you're noticing also, now they went down to 1.79, so remember the limit was 5/3? So what does 5/3 mean? 5/3 really means 1 2/3, so 1.66666, right? So you might be wondering, gee, how far is this going to go down? So one way to do that is to go like this. Go into Window. Well, actually, you could even use your table of values. Let's use the table of values feature, how you had that on Ask. Let's go to Second Table. I'm actually going to delete all the other guys that are in there. And just say, okay, when x is really large, say 58, what is y? Okay, 1.7. Well, how about when x is, how about when x is like 1,000? Let's see what happens. Oh, 1.6693. Okay, how about when x is 10,000? Ah, 1.666. So we are seeing, yeah, that does seem like it's tending towards, 1.6, which is what we found, 5/3. Now let's go in the other direction. What about when x is negative 100? Oh, what about when x is negative 1,000? So when the x values become, or negative 10,000 become infinitely large, that also looks like it's tending towards 1.6 repeater, or 5/3. So you can take that sort of numerical approach, or you can take the algebraic approach. They should sort of jive together like that. Okay, hope that helps. See the next example. Okay, in this next example, it says compare the degree of the top to the degree of the denominator. So I'm going to rewrite the function here so you can see it. Y equals 11x plus 2 over 2x cubed minus 1. So in the last example we did, the degree of the top and the degree of the bottom, the degree of the numerator and the degree of the denominator were the same. So the horizontal asymptote ended up being the ratio of the leading coefficients. Well, in this case, it's not the same, right? The degree of the numerator is smaller than the degree of the denominator. Remember, degree means like the power. So like the degree of the denominator is 3rd degree, degree of the numerator is 1st degree, the degree of the denominator is higher than the degree of the numerator. So I'm just going to note to self here, degree of denom is greater than degree of the numerator. And I'm kind of hoping that you're having memories from pre-calculus about what is the horizontal asymptote when that occurs. You're probably thinking, yeah, the horizontal asymptote always comes to be 0, and you're noticing that from the graph. So as x becomes larger and larger and larger, y is approaching 0. And as x becomes smaller and smaller and smaller, as x moves towards negative infinity, you're not going to go, and my little arrow there is misleading, as x goes towards negative infinity, you're not going to go below that x-axis, okay? We can take, more of an algebraic approach now that we know about limits, so let's go for that. Remember a moment ago we said, why don't you divide by the highest power in the denominator and then take the limit? So if we do that, we have the limit as x approaches infinity, and the highest power in the denominator is x cubed, so let's do 11x over x cubed. Let me erase this y equals here and just operate on this part that we're interested in. So 11x over x cubed plus 2 over x cubed all over 2x cubed over x cubed minus 1 over x cubed. Okay? Well, limit as x approaches infinity, I always think of the dominant, here, this is going to reduce. You're going to have x squared downstairs. This is going to cancel, so you're going to be left with just a 2 downstairs there. And then think about, I'm going to do this in orange here, think about storing a large number, in. Well, if you have 11 over a huge number, positive number squared, this quantity here is going to go to 0. And 2 over a huge number, an infinitely large number, is also going to go to 0. 2 itself here, so far we've got 0 plus 0 over 2, okay? 1 over an infinitely large number is also going to go to 0. So we have 0 plus 0 over 2 minus 0. We're still ending up with 0. So what we're showing is that the limit as x approaches infinity is indeed 0, okay, of that function. Again, we could plop that into our TI-83 and take a look and use that trace feature and verify that the function's going to approach the x-axis and not cross it. But we've taken that algebraic approach as well. All right, let's see the next example. And I did want to mention, I was being a little bit of a lazy mathematician there in terms of writing my limit. So, I would write the limit as x approaches infinity of the function f of x, is equal to this, which is equal to 0. Okay? And likewise with negative infinity, the same thing would happen. The reason why is because if I stick an infinitely large negative number, in the denominator here, it's still going to tend towards 0. And same thing here, if I stick an infinitely large negative number in the denominator, this is still going to go to 0. And here I'll still have 2 in the denominator. So I will, even if I go towards negative infinity, I'm still going to end up at 0 for this. All right, hope that helps. Okay, so more formally from what we've seen, what we gathered so far, a line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches, now note if it says if either the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. So sometimes you'll see the horizontal asymptote existing on the on the right side of the function rather than the left side of the function. And I always wrote here, when in doubt, graph it out. So let's take a look at the next one. This is an interesting one. That's why I wanted to show it here. And that's what I meant by when in doubt, graph it out. We have f of x equals x cubed, minus 2 over absolute value of x cubed plus 1. So the problem is this here absolute value in the denominator. Notice if we do go and graph it, and I am going to put it in my calculator just to show you how to do that, you would see the two horizontal asymptotes. So what we could see here visually is the limit as x approaches infinity of this function So I'm coming, x gets larger and larger and larger, your y values are approaching 1. So the limit as x approaches infinity is 1. But if I come out this direction, limit as x approaches negative infinity is negative 1. So the limit as x approaches negative infinity of the function is equal to negative 1. So it has two horizontal asymptotes. Now, if I'm just pretend the absolute value bars weren't there, right? I mean, you'd have x cubed over x cubed. So the ratio of the leading coefficients basically would be 1. So most people would be inclined to say that there's going to definitely be a horizontal asymptote at 1. But I always say the absolute value makes you account for those two cases. What if x were negative? What if you were basically looking at negative x cubed plus 1? So you investigate the other case. Well, if you're looking at that case, then the ratio of the lead coefficients would be negative 1. But let's just practice to make sure. Let's practice you putting that in your calculator. Okay, make sure you know where all the appropriate buttons are, like your absolute value button. So remember, paren x up caret 3 minus 2. You always want to sort of chunk the numerator and the denominator off with parentheses to be safe, divided by paren absolute value, so math, slide over to num, absolute value of x, so like that, and then you want that whole absolute value of x cubed, so I'm actually going to break that off with an extra set of parentheses. Okay, and I want that absolute value of x cubed, so I'm going to do here up caret 3, okay, and then plus 1. So I always say whatever, function you see sort of graphed in the book, like this one I took from the book, try to make sure you can graph it yourself before the test. Let's count the number of parentheses. 1, 2, 3, 4, 5, 6. Parentheses on bottom, we should be safe. Let's do zoom 6 for starters. Yay! And we are seeing the same thing appear. And like I said, you could trace and zoom in and get a picture that looks an awful lot like the one we see here. See, so I'm just zooming in a little bit closer like that. And if you use that trace feature, like I said, you could just trace out along the curve and visually see that as x gets larger and larger and larger in the negative direction, y is approaching negative 1. So you can see my y values changing there, and they're getting awfully close to negative 1, right? And you could do the same thing in the positive direction, or again, you could take that tabular approach where you're saying, let me delete all those other values that are in there, where you're saying, gee, as x becomes huge, let's say 500, okay, y is converging to 1. Or as x becomes large in the negative direction, say negative 1,000, negative 1. See? Okay, let's try another. Now notice at this moment, I'm not trying to get you too hung up on proving why these are. I really do want you to be good at getting the graph and looking at it graphically and perhaps numerically, the way I just did with the tables. With this example, y equals x sine 1 over x. Later down the road, we're going to learn something called L'Hopital's rule for finding a limit, but I'm going to set aside L'Hopital's rule for now. I just want to explore things graphically. So let's just say we put this in our calculator and took a look. We would see something like this, and we see that it's oscillating so close there as you get towards origin. But here we're not looking at, the limit as x goes towards 0. Now we want to say, hey, what's the limit as x goes towards infinity? So as your x's become bigger and bigger and bigger, what's happened to those y values? Are they capping off? Yes, they are. So we can see the line y equals 1 is a horizontal asymptote of the function. And like I said, later down the road, I'm going to use L'Hopital's rule on this to show that the limit as x approaches infinity is indeed 1. For now, I just want you to get comfortable with graphing that. Okay? Let me hit pause as we do that. So I'll tell you what I like to do. So I typed in x sine 1 over x. I always like to hit zoom trig because it'll usually give you a nice window for, it'll do it for you. So zoom trig. And we see it oscillating in there. It doesn't look like it's oscillating as much as it does on that picture, but if you zoomed in near origin, it would. So, but again, we're not looking at origin in this case. We're looking out, as x gets bigger and bigger and bigger. So I'm using that trace feature. I'm tracing along. My x's are getting bigger. And what's happening to my y's? They look like they're capping off at about, 0.99999, so awfully close to 1. And again, we'll just use that table feature. I'm going to hit delete there of what was in there before, although it is doing that automatically. So as x goes towards 100, look at that, y is going to be 0.99999. And as x climbs to 1,000, it has basically has a round off error and says 1. The calculator says, I give up. It's awfully close to 1. So, all right, hope that helps. Let's see what's next. In this next example, I did want to mention that, we tend to think of an asymptote as an invisible boundary line that never gets crossed, but that's not always the case. It could get crossed infinitely often. So here in this drawing, and again I'll make the function bigger so you can see it, it's 2 plus sine x over x. Here, 2 is a horizontal asymptote, but what's happening is it's getting crossed infinite amount of times, but it's getting, smaller and smaller and smaller and smaller. The distance between the, sort of the height of those waves and that constant line at 2 is becoming smaller and smaller and smaller. But something interesting to notice how the function, just this part here, sine x over x, remember from the sandwich theorem? Notice that sine x over x is bounded above by 1 over x. And we could use the sandwich theorem to investigate the limit as x approaches infinity. So, well, 1 over x, as x approaches infinity, it's the limit 0. So we can see how, in essence, with the sandwich theorem, you're getting 2 plus 0. So we can see that the limit as x approaches infinity on this is going to be 2. Okay? But like I said, at this moment, I'm not going to make you do one like that algebraically. I would have you take a look at the graph, okay? But we could use limit laws to show, coupled with the sandwich theorem, to show algebraically why this function has a limit equal to 2 as x approaches infinity. But for now, just practice graphing that. Okay, let's see what's next. A brief reminder on vertical asymptotes. And this is just sort of reminders from things that you've done in college algebra. You probably recall that, if your function is, say, y equals 1 over x minus 1, maybe you recall that to find the vertical asymptote, you would set the denominator equal to 0 and solve. Well, if you do that, if you solve that, you're going to see that there's going to be a vertical asymptote at 1, which is what we've sketched in right here, okay? So near x equals 1, the function behaves, much like the way the function y equals 1 over x behaves near x equals 0. So it's like a shift, okay? So then the next logical question might be something like this. What's the limit as x approaches its vertical asymptote? We've already explored limits at infinity. Now let's see what happens, as you're approaching your vertical asymptote. So, what's the limit as x approaches, let's say, 1 from the right? Okay, so I'm coming in towards 1 from the right. It's functional values are shooting up. Towards what? Towards positive infinity. Okay? Now, some limit as x approaches 1 from the left. See, now we can go back and start talking about those left-hand and right-hand limits. So as I'm coming in towards 1 from the left, what's happening to those functional values? They're dropping, they're plummeting. So quickly, right, to negative infinity. So we had discussed continuity. It's continuous, but not over its entire domain. And it's definitely not continuous at x equals to 1 because the limit from the left and the limit from the right are not the same. And there is no functional value at x equal to 1. Okay? All right, let's see what's next. of course, formality of language. I'll just read this to you, a definition. So now a line x equals a is a vertical asymptote of the graph of the function f of x if either the limit as x approaches a from the right of f of x is equal to positive or negative infinity, or the limit as x approaches a from the left is equal to positive or negative infinity. And that's where what we were basically saying, the notion of a left-hand or right-hand limit is coming into play there. And we saw that it either shot up or down towards positive or negative infinity there at the vertical asymptote. Okay. Next, we want to consider some trig functions that have vertical asymptotes. There's lots of them that do. Okay, so two functions that might pop into your head is secant and tangent. So I have them both here, but for time's sake, I'm just going to, oops, let me get my pen. I'm just going to zoom in on tangent. So you may be recalling that the vertical asymptotes occur at pi halves, 3 pi halves, k pi halves when k is odd, right? So let's take a look. Over here I wrote a little note to self. What is the limit as x approaches infinity, as x approaches k pi halves when k is odd? So really, as you're coming in towards pi halves, let's say, and I'm coming in from the left. See, if I'm coming in from the left, I'm going to write this. So the limit as x approaches, I'm just going to look at pi halves from the left is equal to, and I didn't write of f of x, but that's definitely equal to what? Positive infinity. But the limit as x approaches pi halves, and I meant to write from the left for the first one. So as I'm coming in towards pi halves from the left, the limit's positive infinity. Now I'll do this in another color. As I'm coming in towards pi halves from the right, what's the limit? Negative infinity. So the right-hand limit and the left-hand limit clearly are not the same, so therefore the overall limit doesn't exist. And here I said, how about when you look at the right-hand limit? So, the overall limit does not exist at these, at k pi halves, when k is odd, at these odd integer multiples of pi halves. But when you look at the right, you could find a right-hand limit, or you could find a left-hand limit, but the overall limit doesn't exist. All right, now the part that I wanted to mention, you can see down here, it's time to try. All of this was building me up. This was just sort of the rules of the game. It's building me up to trying problems from the book with you. But I don't want this podcast to be too long. So I'm going to just mention here briefly, I'm going to go to the virtual book and I'm going to pull up these problems, and in the next podcast I'm going to be working through these problems with you. And that'll be a much shorter podcast because now we know some of the basics of trying to find limits at vertical and horizontal asymptotes respectively. Okay. Good luck.